Yes, good morning. Welcome along. I'm Professor Hal The from the University of Brighton. And these are my homies, Sideshow Dave Campbell and Fireworks Mike Sansom. And what we're here to do is we're here to show you a few of the things that we do, both here in the UK and around the world, which we think will enliven your A-level students and underscore the curriculum. Hey, Mike?
Yeah.
Yeah, okay. But first of all, what we're trying to do also is introduce a lot of diversity into our show and our team. Aren't we, Dave?
Yes, definitely.
So the first thing we'll do is get rid of the white
get
coats.
the white coats away. Yeah.
And press ahead a little bit. Now, I have to do the health and safety discussion before we go any further. And we are doing live science involving loud noises. So if we ask you to put your fingers in your ears, you have to. We are, of course, using fire. And so if in the unexpected event of a reaction getting out of control, I will let you know, and you will leave the auditorium via the fire exits, which is signified by the green little flashes, right after me, Dave, and Mike, of course. All right, okay. Did you burn the floor? In Michael Faraday's footsteps. All right. Okay. Now, first of all, I hate the expression making science fun because it implies the fun isn't already there. But we really enjoy what we're doing, and we hope that infectious enthusiasm will come through at some stage. And I also like learning outcomes. And the first thing we did there was our first learning outcome. That was lycopodium powder, which is just a very finely divided carbohydrate, and it caught fire because of all the surface area. So we've already done some kinetics without even breaking into a sweat. Sorry, Dave, what are you doing, mate?
Just realised, that risk assessment. I hadn't.
Risk
quite,
assessment.
Well,
What is this
risk assessment? I mean, it's the Royal
risk
Institute.
assessment?
Risk assessment.
Oh, risk assessment.
People getting
right,
hurt.
Yeah, and you haven't finished it.
No, this pen. Look, this pen. It's run out of ink.
As teachers, you must come across this all the time. My pen's run out of ink. Are we there yet? Can I go to the toilet? Do you have to put up with that? My pen's run out of ink. No.
Why can't we use a bar? Why does use pens all the time?
Well, anyway, Dave's pen's run out of ink, and chemistry will come to the rescue. Who didn't see that one coming a mile off? Because, and I'm sure you've all guessed it. Yes, I'm sure you've all guessed it. We are going to do the old Briggs-Rauscher reaction.
Oh,
I don't think they know what the Briggs-Rauscher reaction is. It's a modified form of the Belyuzov-Zhabotinsky reaction.
Oh, yeah.
Okay,
Good.
well, we're going to do a reaction to make Dave some ink. It's called the pulsing reaction, and this is a really nice wet chemistry experiment which illustrates autocatalysis and a little bit of kinetics as well. And, of course, it'll make Dave some ink. So solution A and solution B. And I have to point out that 1 time in 5 it fails, normally when Dave's done the preparation for it. So if it doesn't work, then he made it, and if it does work, then I must have made it. So in it goes, and solution C. Now, in this day in which we live, when it's all Xboxes and CGI and animation, I think that your pupils can get a little bit immune to the spectacle. Has that changed colour yet? Oh, it's doing it, isn't it? I think it's a bit of a hot day, actually, so that has gone a darker colour. But let's sort of see what happens. Let's give it a nice little vortex and see what happens. This is one of the most elegant experiments we're going to do. It goes downhill from here, I tell you. So, yeah.
That's not very good as ink, though, is it?
No, it's not. Primarily because it seems to be going clear.
And that's
again.
even worse now.
Well, yeah, it is. Has that changed colour? Did it or did it not go blue? And is it now not the colour? It's yellow. And with a bit of luck, it's going to go blue again. Yeah, yes. Oh, that's. Yeah, okay, well, this will do it 14 or 15 times, and depending on the temperature. And we could stare at it all day, but we haven't got all day, have we, Dave?
No, I was just thinking, one day this could be an oil painting hanging on the... Of us doing the Belyuzov...
Talking about
oil
painting.
They've got oil paintings out there.
Yeah, but it's a wet chemistry experiment. It lasts for like 10 minutes maximum.
Well,
Isn't that cute? Isn't it cute? Yes. Thank you very much for that supplementary round of applause. Yeah, and it will speed up as it goes along. So we've got lots of autocatalysis, and clearly it's two competing reactions, one going one way, making some products, and the products then reacting to go back to the reactants, and sooner or later it'll run out of something. Are you on your eBay page there? Notes? No one's ever done that in one of my lectures before. Really? Wow, I'm stunned. Anyway, so it's a really nice experiment, I think, and it'll carry on doing what it's doing. Like that. for ages, but we need to move on a bit because I think it's an example of kinetics. And kinetics and thermodynamics in particular can be a little bit at variance with this notion of science being fun and being absorbing. And when I did my inaugural lecture, I was trying to find some way of countering that. And I looked something up. I actually looked something up for the first time in a long time, and I've forgotten who said it, but whatever he said, it was very, very good. He said, science is a dazzlingly lit kitchen which can only be accessed by going through a dim and ghastly hall. Isn't that great? I wish I could remember who said that, because it was a really profound thing. And the kinetics and the thermodynamics are the dim and ghastly hall bit, and what we're doing is the great dazzlingly lit kitchen. Isn't it, Dave?
That certainly is, yes. And
which brings me nicely to our next point, because we're going to move from kinetics to thermodynamics, the movement of heat and or energy. And you can do all sorts of reactions to prove this, but we've actually written with the good people of Cleeps a standard operating procedure for this next reaction. So if you want to know how to do it, pick up a card from me later on and we'll explain it. Because in these sort of rather innocent-looking test tubes, there is something which normally gets gasp from amazement and surprise, because we all know that most reactions give out both heat and light. So if I use, let's use a blowtorch. If I use my nice blowtorch here, we know it gives out light because there's nice blue light. And if I put my finger in the middle of the flame, I'll find out all about the heat. Most reactions give out both. Some reactions give out heat only, and a very few reactions give out light only. And we've been working on some of these. Can we have the lights down, please? Because if you mix what's in test tube A with what's in test tube B, that's nice. The teachers are actually saying, oh, like a little pantomime. Yes, these are oxalate esters. Oxalate esters with hydrogen peroxide. And in the excited state, they give out energy, but the heat transition is forbidden, so they can only give out light, which is quite sweet because, yeah, wow, it's blue like my eyes. Look at that. Isn't that great? There's a nice little blue one there. And the minute you do this in a test tube, your pupils will think you're great, and then you can explain to them that it is indeed the chemistry of glow sticks. It's green, this one, like Dave's teeth, as you can see. Can you see that?
Thank you.
And you can actually do this by dismantling glow sticks, which is precisely what we do. And Cleeps have got a standard operating procedure for dismantling glow sticks. It's very, very easy. It takes about 10 minutes to prepare, and your pupils will love you for it. And if you can have the lights down one more time, please, because those are quite impressive, and those will last for about 8 hours. But if you want to really wow them, me and Dave's been working on something very, very special. And this one will take about 5 minutes to... actually, that's really lame. That is quite lame. Why is it so lame?
It's those new ones. I don't think.
Did you use the new ones? Right.
Yeah,
okay, well, that's lamer than I thought it would be. But anyway, the point is, it's chemiluminescence. Chemiluminescence with oxalate esters. You can do it. It's really straightforward, and the class will absolutely love it. So give it up for oxalate esters. We'll speak about that later.
Okay. Yeah,
right, okay. Moving on. Okay, so that's thermodynamics and kinetics. And now we're going to move on to a theme of gases. And doubtless, you talk about all the gas laws in your specification. And we're going to do about 20 minutes of gases. And in particular, some of the physical properties of gases with which you'll be familiar. Now, this is called the methane mamba, and it's dead easy, all right? Or you can do this with a lemonade bottle or any other PET bottle. You just need to cut it about that long, and you've got your receptacle for the methane mamba. Hook it up to a gas tap, and by trial and error with Radox, and this is what Dave's doing, he's bubbling methane gas through Radox, and it's one of the few times that Dave and soap come into close proximity, I have to say. But anyway, the point is, what we're illustrating here is that methane is lighter than air. So isn't that great? Methane gas, Dave?
Yeah.
Producing methane? Oh, I'm so sorry. Dave, this is a Royal Institution. You can't
yeah,
do
know,
that.
I know,
And these are teachers. There'll be no sniggering at the back of this class, mate. Oh, it's a bit droopy, isn't it? Come on, keep... That's better, mate.
There you go.
Right. So the point is that the methane's lighter than air. Yeah, calm down.
Okay, I'm going, sorry, I'm going carried
It's
away.
getting all excited now, look. The methane's lighter than air, and it's supporting a column of foam. And at the top, the methane's diffusing out and air's diffusing in, so it's going to turn a bit droopy. Now, sometimes it looks a bit like a methane seahorse or a methane slug, but the name of the reaction is the methane mamba. And if you're very, very good, and Dave is very, very good sometimes, all right, just watch that because it'll pinch off there, mate. You can take... No, that's rubbish. You can take a mamba for a walk. No, we meant to do it. It's all right. It's quite all right, yes. Now, the reason that Dave's hand didn't get all burnt up is that there's very little oxygen in the column and it's burning away. But his skin is so baby smooth, and he saves
This one. Sorry.
and he saves a fortune on IMAC. And no, you can do it. You can do it in the classroom, and it's a really nice experiment. It shows all these properties, doesn't it, Dave?
It certainly does, but that wasn't... you have to get the soap mixture. It's quite...
It worked fine for me earlier.
Yeah,
but it always works. Yeah, but it always works first time, and then...
All right, okay. Right, okay, let's move on. So we're going to stick with our theme of gases and lighter than air and heavier than air and all. And in this very room at Christmas, Pete Walters talked about helium gas. And he's got a bee in his bonnet about helium gas. And I have to say I share it. You know, because helium's lighter than air. You all know this. And you know those big heart-shaped balloons you get on Valentine's Day? Well, I didn't get any. Anyway, the point is that two things. First of all, you let go of them and they fly off into the atmosphere. Or, of course, you cut them and you suck the gas in and your voice goes all high and it's very, very funny, which, of course, you shouldn't do. And the point is that helium gas, it comes from the ground, not from the fractional distillation of air. And it all comes from the alpha decay in the uranium decay chain. And when it's gone, it's gone. And we need helium gas because it boils at 4.2 Kelvin for our PET machines and our CT scanners, not for silly, frivolous things like singing songs.
No.
Now, we've got some here, and in the spirit of true scientific discovery, we are going to breathe some in and sing a song, after which there would be, of course, thunderous applause. But we also thought that we could go the other way. Helium makes your voice go up in pitch because it's less dense than air, and so your larynx vibrates faster than it normally does, and your voice goes up in pitch. If you take a gas that's heavier than air, presumably the same thing should happen, but in reverse. Your larynx should vibrate slower, and your voice should go down in pitch, or so the theory goes. And such a gas might be argon or sulfur hexafluoride, which is what we're going to use. Now, I have to say, we've done this several times on TV and in live shows, and somebody always grizzles about it. So if you're ever going to do anything like this in your classroom, you must tell your pupils not to breathe in gases other than air, which, of course, they should breathe in at the normal rate for the rest of their lives. But, of course, you shouldn't have them breathing in any unusual gases, else who knows what can happen. So anyway, we're going to do this in the spirit of knowledge gathering and pushing the frontiers forward. Have you switched this on, have you?
Yeah, just do it there.
Right.
Okay.
So we're going to sing this song, are we?
This song, yeah. That's
Well,
hard.
turn it on for me, will you?
Yeah. Well, no,
Well,
go on. Go on. Yeah, there you go.
No sniggering at the back, please. Shall we sing the song?
Yeah, let's get it going because it takes time. Take it again. Okay.
And now the end is near.
And so I face the final curtain.
My friend, I'll say it clear.
I'll state my case, of which I'm certain.
I've lived a life that's full.
I've traveled each and every highway and more, much more than this.
We
Did it my way. Thank you, thank you.
Thank you,
Oh,
thank you,
oh, oh. Whew.
Are you all right, Dave? Yeah.
Dave, the chairman of the board, old blue eyes. Now, I have to say that Dave gets the raw end of that experiment because helium does indeed cross the blood-brain barrier. No
Right,
more,
good.
no more. All right, it does cross the blood-brain barrier, And the point I was making earlier is that once it's in the atmosphere, it's so small and so fast that it reaches escape velocity and it goes into space. That's why it's, excuse me, that's why it's such a waste. And I had to breathe in and out a gas that was 6 times heavier than air, so I had a challenge as well. Wasn't it great? I love it,
It's like
Dave.
singing the old song again.
It is great, isn't it? Anyway, we're going to press on with our theme of sulfur hexafluoride and with this here tank. And I can feel a nautical theme coming on. Come on, work the audience, Dave.
Come on. Audience participation, I know.
Yeah, please.
And they're all keeping time. I like it. It's good.
I have to say, I like that sort of token clapping. That. See, I'm far too dignified for this. I'm not going to clap along Professor Hal's song here. Right, okay, I just want to adjust my hat to a more rakish angle. Is that rakish or jaunty? Jaunty. I wanted it rakish. Right, okay, how interesting can it be? Okay, this is a sulfur hexafluoride boat. And I know what you're thinking. You're thinking, well, you know, where am I going to get sulfur hexafluoride from? And there's nothing we're going to do today that you can't do. And we've built this up over a number of years, but we started with absolutely nothing, didn't we, Mike? Absolutely nothing, all right? We just came along one day with nothing, and we built it up over time. And anyway, Dave, oh, I like it, Dave. Dave has made a boat here, HMS Ark Royal Institute. A little play on words there, all right. How interesting can it be? All right, do we need a scrutineer? Have we got any safety glasses? We need a scrutineer, don't we? No, come on, we need a scrutineer. Step this way. What's your name, please? Amna. Yeah, give it up for Amna. Got any safety glasses? Now, don't belittle the audience. Right, we'll assume safety glasses for the time being, all right? Now, Amna, what we need you to do is you can stand there with Dave, please, all right? And you're going to launch our boat because we've got something in here which is heavier than air, and we've got a boat, and boats float because of Archimedes' upthrust principle, something like that.
Lift this up, right? And then,
so anyway,
so if you hang on to it, if you just hang on to the
right?
edge of it, yeah, that's fine.
Have you ever launched a boat before?
Come on,
It's really straightforward. It's like a
okay.
right. So lift it up,
and then you just gently push it down. That's it. Push it.
Yes.
Right now.
That's right. Coming nice and close on the boat. Isn't that good? Now, can you confirm there's no little strings here? There's no strings. All right. So, and we can take the boat out. And could you put it back in for us, please? Nice and gently. Just lay the boat in there so you can see it's not any chicanery or charlatanism. Because, no, it's straightforward. There's SF6, which is 6 times heavier than air, and a boat containing air. That's all right. You can go now if you want. It's not gonna... Well done.
Thank you very much.
And it'll float. And I've floated Dave's boat, it would appear. Schoolboy humour, isn't it? Like, you must be learning this from your pupils. Now, having floated Dave's boat, I think, technically I'm bailing in, not bailing out. Isn't that right?
It's just going down.
A bit of respect. She is going down, actually. Come on. Sink, damn you. It is a good boat. You're too buoyant. Oh, for goodness, I can't be bothered with that. Give it up for the boat, please. What did you say? Clouds. Clouds. All right, okay. So we're going to move on now. And like I said, there's nothing. I'm going to make a nice cup of tea while we're here. There's nothing here that we're going to do that you can't do. And the reagents are, I will say, freely available. Yeah. And so we're going to move on with our theme of gases with this gas. And this gas, well, we all know the triumvirate of solid, liquid, gas phase, don't we? Solids, liquids, and gases. We all happy with that? It's all right. Didn't want to be seen. Okay, so by the way, do you like this? Dave brought this. This is so retro, so tatty, it's good. And where did you buy it from? What? A charity shop.
Come on, leave it alone.
No, you bought a second-hand, whatever it is, ice dispenser. It's so Del Boy, isn't it? Now, Raquel. Right, okay. Anyway, so ice water, and we'll call it steam, even though we know it's not steam. Gaseous water, whatever the name for that is. Ice melts to give water, water boils, steam condenses, and ice freezes, or whatever. Anyway, the states of matter. This, as you know, you probably maybe don't know, this is carbon dioxide, which bypasses the liquid phase. And it's probably easier and inexpensive to get, more easy to get and inexpensive than you might think. And you can do some really elegant science. The thing is, it's cold. And when you have your little pupils throwing snowballs and they get cold fingers from the ice, that's at 0 degrees. This is at the temperature, colder even than Dave's front room in the middle of winter, at a dreadfully cold cryogenic temperature of minus 78!
There wasn't...
Yeah, that needs to be a bit louder, doesn't it? Else it doesn't convey the terror of minus 78. All right, so if you're going to handle it, you have to keep it moving around so you don't get horrible frostbite on your fingers. And, of course, what you mustn't do is put it in your mouth, because then you get
the risk assessment, don't eat... Oh, I didn't write that bit down. Sorry.
Well, you should have told me not to eat CO2. You know how easily led I am.
Yeah.
Anyway, you can do some really, really elegant science with CO2. Really elegant science. This one. Right, okay. All you need is some boiling water or some hot water, and you can show about 5 learning outcomes. 5 in one little experiment. Right. In it goes. Now, the first learning outcome, you get a great big handful of this, and you stick it in there. And off it goes, all right? It goes absolutely berserk. And the white stuff is water vapor because the CO2 is so cold. But straight away, you can see it's subliming, turning straight from a solid to a gas. Now, the next learning outcome you can see is where's it going, up or down? Down, all right? So we've just illustrated that carbon dioxide is denser than air because it's dragging the water vapor down with it. And the third, and I think this is one of the most valuable, is that I put in 2 hands full... What a rubbish glove that was. Give me another glove. Well, it just popped like that, didn't it? It's supposed to get all big and turgid and... Oh, that's more like it. Right, so we put in 1 handful of CO2, well, maybe 1.5, and you can see that it's turning into an awful lot more than 1 handful of gas. And we're just illustrating that gases... Oh, sweet. We're just illustrating that gases occupy much more space than solids. Okay, 1 mole occupies 24 litres. I put in much more than 44 grams of CO2, and it's... Well, when it pops, you can give me a big hand, can't you? Big hand. Don't worry, we've got another one. It's lucky I had another one, isn't it? You're right there, mate. It's there, look, right. Right, OK, this is a good quality glove, and it's lasting a long time. So we can, we can do the old... Yes, give it a nice round of applause. Right, and Dave's brought me, and I keep losing my box of Cook's matches, and I hate myself for doing this because carbon dioxide also puts fires out, and which is slightly against my nature. So in it goes, and out it goes. And it sort of reminds me a little bit. Come here, Dave, please.
What? Okay.
It reminds me a little bit of quite a nice experiment we do. Dave, I know I've been riding it back a lot recently, and what I thought I'd do is I went down, there's a fine tailor down the road, so I had a nice bespoke jacket made for you. Isn't that nice? There you go. There you go. Now,
this would look good on the oil painting, couldn't it?
Yeah, absolutely, yeah. Now, why don't you look at that? It's a nice example of a Royal Institution door there. So why don't you just look at that for a bit and just savour the craftsmanship while I explain the next experiment. Okay. Now, I'm not sure, but when I was at school, it was a standard break time sport to let the fire extinguishers off. And today's going to be no different, except this is my fire extinguisher, which I bought with the sole purpose of shooting Dave in the back. Dave, the door, mate, the door. I'm talking about you, not to you, all right? Now, you can demonstrate adiabatic expansions quite nicely using a fire extinguisher, because inside this fire extinguisher is carbon dioxide under pressure, but at room temperature. And in a minute, I'm going to shoot Dave in the back with it. No, Dave, the door, mate, the door. And when I do that, the CO2 is going to expand and turn into a gas. And in so doing, it's going to push back the atmosphere, which costs it energy. It needs energy to do work. and it hasn't got time to get that energy from its environment. So it uses its own internal energy, and that's going to have an effect on it, all right? So 3, 2, 1. Right, so Dave's back's got a big white stain on it. Can we show the big white stain to everyone? Isn't that great? And you might think that's ice, but it's not. That is solid CO2 at minus 78. Well, minus 77, but who's counting? Because it's got so cold, it's turned from a gas into a solid. And how's your back, Dave?
Yeah, it's because I pulled it earlier when I was lifting that stuff in, and that seems to
Wow.
sorted it
What,
out.
what a versatile gas. It sorts Dave's back out. Well done, Dave and his big back. Well, for our next item, and I can't actually remember sending all my risk assessments for this one. Actually, I can't remember sending risk assessments for anything at all. But I'm sure we would have got pulled up for this next experiment. And, well, I mean, if it isn't written down, it didn't happen, did it? When I was teaching at a prep school, this is years ago, 1995, I think, I actually did this experiment because I was doing my PhD there. And we managed to break those really sturdy old lab stools with it. So you too can do that, break your equipment and cause massive explosions. And one time, actually, we did it in the school field. We were trying to use this experiment to measure the speed of sound, and the police turned up because it was and they were actually relatively understanding about it. Can you start filling that up, mate? Because what I thought we'd do is we are going to put some solid carbon dioxide in that bottle there, and that bottle is made of polyethylene terephthalate, and they're built to withstand about 3 to 5 atmospheres because they contain carbonated drinks. And CO2, if you put it in there with some boiling water, can generate up to 50 atmospheres. So what we're going to do is we're going to put CO2 in, and then we're going to put boiling water in, and then all the boiling water is going to splash out all over me and Dave, probably deforming me terribly. But my kids will understand. You understand? Deforming Dr. Hal terribly. Got that? Right, okay. My kids will understand as long as you're learning some science to show your pupils and stuff. And then there'll be a big explosion. Oh, sorry, I forgot to turn my phone off. No, seriously, I did. No, I did. It's an iPhone. Hello?
Hello?
Hello.
Oh, is that Professor Sosabowski?
Yes, it is.
Oh, this is the safety officer for the Royal Institute.
It's a safety officer. Yes, what do you want?
Yes, well, I hear you're going to be doing that rather dangerous experiment.
Yeah, it's only a few teachers. They knew the risk when they walked in the door.
This is the exploding bottle, is that correct?
That's the one.
This is the Royal Institute. You cannot possibly do something like that here. It's out of the question. Far too dangerous.
Everyone look at Dave.
Are you listening to me?
So you say we can't do it?
Yeah, yes, you can't do it, okay? You promised me you won't do it then.
Oh, I promise.
All right, then. Well, I'll trust you won't do it, then I'll say goodbye then.
Okay, bye-bye.
All right, well, you put the phone down first.
No, you put the phone down first.
No, you put the phone down first.
No, all right, I'll put the phone down first.
All right, well, goodbye.
Bye-bye.
I love you.
Love you too.
Okay.
Guess what, Dave?
Not.
That was the Royal Institute safety officer.
Obviously we can't do it. It's
No,
ridiculous.
but I hate it. When my phone goes off, it's either the coroner or the police or the other coroner. I hate that guy. He's always phoning me up, always moaning about explosions, control measure this, certain death that, who can be harmed this. Anyway, we can't do it. We can't do
That's a shame.
exploding bottle. It's the best item in the whole show. Didn't you say you were the boss today? You are, aren't you? Allegedly. What does it say here? Your title? You're the curriculum qualifications team manager. That sounds quite impressive. So you could make an executive decision that we could do it, couldn't you?
I'll put the glove in.
And you, huh? Oh, go on, because then there's the teachers. It's the end of term, isn't it? End of term treat. That sounded like a yes to me. Right, okay. Right, so we are going to do the exploding bottle, right? And we've got some safety shields. So they said, you've got to have some safety. You've got to have some safety. Right, okay. So let's remind you what we're going to do, all right? Right, I bet you're sorry you're sitting there now, aren't you? Right, we're going to put boiling water in here, all right? And the CO2 is going to sublime and turn into a gas which wants to occupy more volume, but there won't be any more volume because I will have put the top on. And therefore, instead of volume going up, it's going to be the pressure that goes up. And after a while, well, we all know what's going to happen. When you're doing this, if you want some little sort of chat to fill in the gaps, just show your pupils, and I know I should get out more, but I'm fascinated by this. When they first brought out soda bottles, people used to get shot in the eye with the lid. You'd take the lid off, And then when you took the thread off, the pressure would shoot the lid into your eye. And so what they've done now, they put little cuts in the thread, and they've put cuts in the thread on the lid. So when you undo it by a quarter of a turn, the cuts line up, and you hear that satisfying little hiss, but the thread's still engaged, so it doesn't shoot off and blind you in the eye. Isn't that great? I think it's great. I don't think it's great. Well, I know, but it's a really clever thing. I wouldn't have thought of that. Anyway, what you might... Oh, yes, the death knell of... Right, okay. So what you might like to do is play some large it up music. So what have you got there, Mike?
Right. God, it's so...
No, we need large up music, mate. All right, let's go. Let's go, Dave.
Right,
go,
okay.
go. Come on, mate. Keep pouring.
I'm pouring. I can't see anything.
I can't hold it, Dave. She's breaking up. She's breaking up.
No, it's okay. I'm still pouring.
Keep going. That's enough.
Enough.
Right, take the funnel off me. Take it. Right, you might want to put your fingers in your ears now. Oh, how about that one? Oh. Where did it go? Has it shot someone? Where did it go? Is it on the roof? It's behind you. It's not a pantomime. Where is it? Where's the bottle? No, it's not.
Oh.
This is supposed to be teachers. Look at that. Isn't that great? Oh, yes. Who's your daddy now? Look at that one. Yeah. Chemistry has the answer. So, the exploding bottle. And they'll love that. Pressure, volume, temperature. It was all in there, wasn't it, Dave?
Yes, it was.
Sublimation.
Yeah.
You name
danger.
it. And danger.
Danger.
And we love danger, don't we, Dave?
Yes.
Yes. Right, okay. So, there you have it. That's CO2, and you can do all of that stuff in the classroom, or you might want to do the bottle outside, but so much the better. And there's a video with a full risk assessment on Teachers TV, or what used to be Teachers TV, that we've done. It's called... The exploding bottle, I think.
Yeah, I think it is called the exploding bottle.
It's called,
exploding bottle experiment.
Yeah, just Google Dr. Hal exploding bottle and you'll find it. Anyway, that's CO2, all right? And I'm sure you didn't traipse all the way up here just to see minus 78. Oh, no, you want something colder than minus 78. And we've got the very thing. Because in here, we've taken the very air around you and we've cooled it down by Joule Thomson cooling, probably, till it's turned into a liquid. And it's colder than minus 78. This here is liquid nitrogen at a terrible, terrible cryogenic temperature of minus 196! I like the way that the volume sort of goes up halfway through that. Right, okay, let's move on. Right, so we've got liquid nitrogen here. Now, liquid nitrogen, it's actually one of those things, it's curiously compelling, and it's also... deceptively dangerous, or is it deceptively safe? What is it when it looks safe, but actually it's not safe? Deceptively safe. Is that right? Or is it deceptively dangerous? Deceptively dangerous. Anyway, the point is it's deceptive. All right, okay. Now, liquid nitrogen boils at a temperature of minus 196. So therefore, that is boiling at the temperature of the glass. Okay? The outside of the glass is at room temperature. The inside of the glass is at minus 196. And very shortly, that's going to reach equilibrium, which is what it's doing now, and it's calming down. And the little boiling that you see is just what we can't avoid because this is an unsilvered dewar. Now, you can do lots and lots of interesting science with liquid nitrogen, and providing you've done the merest of training, but you need to be properly trained in it, you can use it. Now, once again, I'll draw your attention to Dave's ice container, which he was very pleased about it. You went out of your way to find it and look it out because it contains ice. And if you ask your pupils, what does boiling mean? I suspect they'll say it means hot, something to do with hotness. And you can reevaluate and redefine their definition of boiling forever by doing an experiment like this. Because we're going to use the temperature, the heat capacity of ice cubes to boil something. Because if I put ice cubes at 0 degrees into liquid nitrogen, 0 degrees, maybe 0 degrees, but what temperature does that boil at? Minus 196. In a room full of teachers, and someone's got... It better not be the safety officer. Yes, 0 degrees is still 196 degrees hotter than the boiling point of the nitrogen. Is that not so? And so if we put the ice cubes into the nitrogen, it would indeed cause it to boil. It's like putting red hot iron into water. It will cause it to boil because they have a heat capacity which exceeds the boiling point of the liquid nitrogen. I think that's a stunning experiment. We're using ice to boil something. We're using a cold thing to boil an even colder thing. I know I'm going on about it, and I should get over it, because it's not that great, but I think it is that great. Isn't it that great?
It is great. Come on.
No, it is. I know. I know that, and you know that. Huh? We haven't got time to say how great it is. We need to move on. All right, so now, there's lots of other stuff we can do with liquid nitrogen, and I told you all about Dave's personal hygiene problem, and we can resolve that right now, because the other thing I always tell him is he needs to take a cold shower, and you know what I mean, don't you? No, I don't know what you mean. Cold shower, what does that mean? A cold shower. We can use this now. This looks like a load of copper tubes bolted together, but it's my soon-to-be patented liquid nitrogen shower, because these are, again, 196 degrees above the boiling point of the liquid nitrogen. So if I stick them in, I think, Dave, I've known you long enough to have a shower together. Oh, isn't that nice? Very refreshing. That is actually, that's very
so
refreshing.
cool.
It is so cool. Yes.
Very nice.
And it keeps the dandruff away.
Yeah, everything.
No visible
freezes
flakes
it
at
off,
3
yes.
feet, and gives my hair life and bounce, and my split
nice.
ends all go. And so, isn't that great? Yes, again, because you're really too kind. Now, there's 2 more things we're going to show you with liquid nitrogen. And the first thing is, we thought, because this was such an auspicious occasion, we'd come and just do chemistry. But when we do stuff for OCR from time to time, they said, Hal, there's other sciences. I said, is there? So don't just do chemistry, broaden your act. Do some biology. And I said, well, we can't catch butterflies in the Royal Institution. There aren't any. And then they said the F word. That was your cue for the da-da-da. Yes, physics. They said, do some physics. Now, so I thought we would do some physics. Where's the balloon gone? Has it popped already?
No.
Right, okay. I thought we could do some physics, all right, as a passing nod. Don't get me started on physics. The physicists invented the Large Hadron Collider, and after about 1 month, it broke. It did, it broke, and they hadn't taken out the extended warranty. So, no, seriously, they hadn't, and it's still broken, I think. So it wouldn't happen in the chemistry lab. Anyway, thank you, mate. Anyway, Charles's law. We all know Charles's law? Yes. The volume and the temperature of a gas are proportional, i.e. the colder it gets, the smaller it gets. We normally get, there's always the one sniggering at the back.
Yeah.
Would you be so kind as to share your joke with the rest of the class? That's sweet. Okay. Now, Charles's law says that gases will shrink if they're cooled down. And I thought we could use this balloon, which I found lying around the RI, just down there, actually, yeah, to demonstrate this.
Yeah, hang on. That was my balloon.
What do you mean that was my
That
balloon?
was my birthday balloon. I just was leaving there temporarily. Take home.
What a baby.
Oh, no, you
Look,
can't put
my
it in
pen's
there.
run out of it. Yes, we
What?
can.
What?
It's a sacrifice they're prepared to make, Dave,
but
all right?
Yeah,
No,
but
no.
you'll destroy it.
No,
if it goes in
Dave,
there.
you're a balloon donor, all right? Get over it. All right, so in it
oh,
goes into the terrible cryogenic power of the liquid nitrogen.
Oh, it's my balloon.
He's snivelling like a little baby.
Oh, I saved up all the money you gave me to buy that balloon.
Oh, Dave, it's shrinking, it's withering like your hopes and dreams, mate.
Oh, no, it's gone.
Look, it's going. Are you getting this? Look. Oh, my fingers.
I want my balloon back.
Oh.
Oh, it's finished. Nothing can survive in there. Oh, they're laughing. It's not fair.
I'm sorry, Dave. Good snivelling, mate. Hang on a minute. Before we go on too much further, all right, in the one physics lesson I did pay attention to, this is good snivelling. He's been practicing that for years. He's just about got it right. I did learn that Charles's law works both ways. If you take the withered, shrunk balloon out and you blow on it, the air inside it should re-equilibrate with ambient temperature, and the balloon should expand all by itself. Look, we can write an article about it, Dave. It says
Oh,
Happy
it's
Earth.
fantastic. Oh, that's brilliant. I can take it back.
It says
That's
Happy
my-
Earth Day now,
oh,
doesn't
it's
it?
great. Fantastic.
Isn't that great?
Fantastic. Oh,
Yeah. Yeah, Charles has got it. So the volume and the temperature of a gas are indeed proportional. I'm sorry about your balloon there, Dave. All right, okay. Now, we're going to move on a bit. And this next experiment is one of those experiments, I don't quite trust it. It's a bit like a much-loved family Rottweiler. I mean, you kind of look at it and you like it and you want to look after it, but you wouldn't leave it alone with your children, would you? No. And we've been doing this experiment for about these whole experiments for about 15 years. Oh, we haven't done the exposition, have we?
It's all right. We're running out of time.
Are we running out of time? Okay, well, we'll come back to that in a bit. All right. Anyway, the point is that we're using 2 deadly elements for this one experiment. Isn't that great? Two elements masquerading as death, all right? And one of them we're going to make for you right in front of your very eyes, because we're going to take from the air around us the terrible oxidizing power of liquid oxygen. Oh, that's better. Yes. Now, we discussed the boiling point of liquid nitrogen, didn't we? Which is? That's great, isn't it? Minus 196. And what's the boiling point of liquid oxygen? Minus 180. So if the boiling point of liquid oxygen is minus 180 and liquid nitrogen's at minus 196, and you pass oxygen gas through liquid nitrogen, it finds itself in an environment 16 degrees above its boiling point, which is also its condensation point. And therefore, it should turn from a gas into a liquid. And we have such a piece of apparatus right here. This curly-whirly copper pipe here has got gaseous oxygen flowing through it. And as it cools down, the oxygen is going to flow through it and find itself in a cooler and cooler environment. And at some point, it will start to condense. Is it started to condense yet, Mike? It's just started now. Now, we've got a special little test tubey Dewar. It's called a Dewar because the person that discovered this, of course, was James Dewar. And I bet there's a picture of him somewhere in the RI. Anyway, you probably can see, if you're on this side, and if that side you can't, but you will, I'll show you in a minute, so it's all right. You can probably see a liquid forming, all right? And that is liquid oxygen. Liquid oxygen. I mean, gaseous oxygen, it's part of the environment or part of the atmosphere, and that promotes combustion. Imagine what liquid oxygen does. Liquid oxygen is what made the space shuttle Challenger explode. Once the liquid oxygen and the liquid hydrogen combined, that was that. It was all over because it's such a powerful oxidant. It's taking its sweet time about it. Does anyone know about why liquid oxygen has got, what is the color of liquid oxygen? It's blue. Does anyone know why? Does anyone want to know why? Unpaired electrons. You need 2 oxygen molecules to bump together and receive a photon of light. And because you've got unpaired electrons, it goes from the oxygen triplet to the oxygen singlet state. And it means that the light that's left is blue light. And it's one of the few elements to have color. Others include chlorine, bromine, gold, silver, etc., etc., etc. So can you see that? Liquid oxygen's blue. All right? It's saying, look at me, I'm so innocent and blue. But if I got this on my lab coat and it caught fire, don't even bother getting the fire extinguisher because you've got fuel and you've got the oxidant. And I'll just get some popcorn and watch me writhing on the floor in absolute agony. All right? Because there's no point because it's fuel and it's oxidant. Yeah, try to look intrepid with my liquid oxygen. Now, we're going to put the liquid oxygen in this big piece of kit here. Now, this is, you don't have to have a big piece of glass like this, but we do because, I don't know, it looks like really impressive, doesn't it? I bet you walked in and thought anyone with a big piece of glass like that must know some chemistry. Your first mistake. Right, okay. So we're going to push the oxygen around, and again, it's finding itself touching something that's well above its boiling point, so it's boiling away. And I just wanted to make a pure oxygen environment in this big piece of glass where I could have piped in some oxygen, but then I think liquid oxygen is a really elegant experiment to do, and now you've seen liquid oxygen. Now, the reason we're taking our time over this is because what we're going to burn in this is bad enough burning in gaseous oxygen, but I ain't going to burn it in liquid oxygen. I'd pay money to see someone else do it, though. That's for sure. All right, because in here, we've got a little packet of death as well. Isn't that, look at that, Dave, all innocent and smiling. And even the label is all like, the label has even died. It's got no label on it. Because in here, we've got the devil's element, the evil element. I'm talking about the terrible killing nature of white phosphorus. Yes, now as you all know, there are 3 allotropes of phosphorus: white, red, and black. And red is okay, and you can do this experiment with red phosphorus, but we think we're large-up chemists and we want to strut around using white phosphorus. And white phosphorus is very difficult to get hold of. In fact, we get ours from a bloke called Malcolm. Huh? Yeah, and he says, whenever I say, hello, Malcolm, he says, no names. And it's always in a pub car park, and he takes cash only, and he doesn't give receipts. And because it's like a chemical weapon, isn't it? Now, the point about white phosphorus is it spontaneously combusts in air because it's so unstable. So my first challenge is getting it into the receptacle, which I've done with no fatalities. Woo! Another good week this week. And what we're going to do is we're going to give it a shove in the right direction by using a hot copper rod. And once it starts, we'll have the lights down, please. So we'll just touch it. Oh, look at that. And this is a very, very classic chemistry experiment. Lights off, please. Because you can see the phosphorus pentoxide forming and the phosphorus burning. It's not that hot. Well, the glass isn't that hot anyway. And in a little while, you're going to get some nucleation at the bottom of the cloud where the phosphorus pentoxide starts nucleating. I said nucleating twice there, didn't I? Which looks a little bit like a jellyfish. Now, don't worry about the smoke. That's only phosphorus pentoxide, which when dissolved in the fluid in your lungs will turn into phosphoric acid and drop the pH to just about 1. So it's probably quite a... this is how phosphorus grenades work, isn't it, Mike? Yes. Yes. That's a good one, actually. It's lasting a long time. A long time. A very long time. And good night. Isn't that great? Dogs? Well, we're coming towards the end of our little demonstration. And the point who said that? Right, I'm keeping you all behind until someone owns up. And then there's detention. No, it is hard because there's so much more to discuss, but you've got loads of other stuff to do today, and we've got our 50 minutes the same as everyone else. The point is, there's nothing we've done here that you can't do. I know sometimes you need some equipment or you need to improvise, but the biggest thing is basically meeting the challenge. And a lot of these experiments, like that one, I remember I did that one for the first time. My hands were shaking, and I was sweating, and I was all frightened of it. And after a while, you get that sort of casual indifference by practice. And I am absolutely sure that if you make the effort to try something like this or try something new, your pupils will love you for it, and you can often underline a point spectacularly, such as with our next experiment, which is one of our most elegant ones, again, with lots and lots of learning outcomes, because I've got the biggest test tubes in Brighton. One day I'll get that wrong. I will. I will. I'll turn the joke on its head, all right? And here's the proof. This is called the barking dog experiment. It's called the barking dog experiment for reasons which will become self-evident. But what I've got in here is nitrous oxide. And if you look up all the literature, it'll tend to say you use nitric oxide. And nitric oxide is a right old pain, because as you know, nitric oxide turns into nitrogen dioxide, which if you breathe it in causes edema in your lungs, and it's really dangerous. But you can also do it with nitric oxide, which you can get in a cylinder, which is completely inexpensive and completely safe, and used to be, didn't Humphrey Davy get addicted to it? Because it's laughing gas, isn't it? It's laughing gas, all right? And it's a very powerful oxidant, and we're going to use it for our next experiment, which is the barking dog. And we're going to use it as the oxidant for our next experiment. Now, the fuel is going to be carbon disulfide, which, like most sulfur compounds, smells like doggy dollops. So when you get that horrible smell rolling towards you, as you will shortly, on this one occasion, it's not Dave, all right? It's the chemistry, all right? And all the people go, ooh, that smells, and that... It's what? Yeah, and it's supposed to smell. So here's what you're looking for. When we light it, and it it's an explosion, effectively. You're going to get a blue flame going down the tube. And as it goes down the tube, it compresses the gas ahead of it. And if we compress gases, they get hotter. And at some point, they get so hot, it'll spontaneously combust. It'll spontaneously detonate the residue of the gases. And that's a diesel explosion. And that illustrates diesel explosions, explosions which are caused by compression, not by any sort of spark plug. And that's how your diesel engine works. So I'll give it one more turn, and then we'll do the little barking dog. So if we can have the lights off, please. Okay. 3. Oh.
There you go.
Thank you. That's better. 3, 2, 1. Right, lights back on, please. Right, okay. So as you can see, first of all, we had a nice blue flash. And I think there's actually an out-of-date patent which used this as a camera flash. It's a rubbish idea, but someone did patent it. And you can see a nice coating of yellow sulfur from the oxidized carbon disulfide. Now, I think that was okay as a starting point, but this is the Royal Institution, and you've come all the way over here to see some large up experiments. So I think we can go a little bit bigger. Now, that is a big test tube. Right, okay. Well, we'll try with this size. And we use the safety shields, of course, because it is an explosion. Once it explodes down there, it has to push the whole atmosphere back. And so there is an outside chance of the tube rupturing. But if it does so, it's likely to do so at the bottom of the tube and not at the top of the tube. So we'll shake this one up again and see what happens. And it's only happened to me once in about 13 years. And actually, yeah, we tried when we actually welded, Mike welded two tubes together, and it didn't even get halfway down the tube. It's just the funniest thing ever. Right, okay. No, it was. What?
Yeah, all right.
Dave's Tourette syndrome just kicked in there. Right, okay. So let's have the lights off again, please. And 3, 2, 1. Right, okay. I think that went quite well. Well, I have to say that was a nice one, a nice bang to finish off with. But you remind me in some respects of some diners who've gone out to a nice restaurant. You've had your starter and your main course and your dessert and a nice cigar with some brandy afterwards. But there's just something missing. So should we, we've got the other one, the one we... I know. But they won't know, will they?
No, that's true.
Come on.
Okay.
You won't be laughing in a minute. No. Now that is a whopper, Dave. Have the lights off, please. Right now, the secret of great science is, of course, all in the timing. Oh. That was crap. Right, if you like this show, I'm Professor Hal. If you didn't like it, his name's Sideshow Dave.
Thank you.
And if you've got any life-threatening injuries, that's Mike from Brighton Fireworks. I'll hand now back to your host. Thank you very much.
Can you let us into the secret about the first one, making the ink, the reversible reactions? Should you give away your secrets?
That's not a secret. It's the Briggs-Rauscher reaction. And it's well documented on, just look on Wikipedia. There's several different kinds. They're called pulsing reactions. But I think actually Kleeps have got an SOP for doing this. And it's relatively common. How long does it take to prepare the solutions, Dave? Takes Dave an hour and takes you 10 minutes, is it? Well, that's what he was implying. I didn't say it. So it's like it produces iodide, but it's a bit more complicated than that. So yeah, it's well documented. Look for pulsing reaction on Wikipedia and start from there.
And different concentrations can make the rate change quite dramatically.
Yeah, so I mean, it's often nice to use the iodine clock. You start off with the iodine clock to talk about concentrations, and you have that as a second one to start with.
When you were breathing in the helium, what happens if you carry on breathing it in?
You faint.
Yes.
No, you faint. What happens is it's quite common. Because your lungs are full of helium, not full of air, even if you hold your breath, you can hold your breath for, say, a minute, because you've still got oxygen diffusing from your inhaled breath. If you've got helium, you've got nothing diffusing. So very quickly you get that rushing noise in your ears, and you can faint, which is why I was standing next to him.
What I was looking out for is Dave's blue lips. If they go too blue, then...
You get blue lips. I don't know why you get blue lips, but you do.
The sulfur hexafluoride, you said that's...
No, that's
fine.
same story. I think that's sulfur hexafluoride. I always think it's quite a bit easier because I don't think it crosses the blood-brain barrier, so you don't get sort of that Overton Mayer kind of anesthesia, but you still get hypoxia. So once or twice I've had that sort of rushing in my ears and. Yes, sir.
With the barking dog experiment, have the tubes got a life expectancy? Can you use them so many times before you replace them, or do you just keep going?
You look at them through polarized glasses, and you can actually see the weak points. So yes, they do have a life expectancy, but you can do it probably 50 times in each tube.
Yeah, they're surprisingly robust, actually. I think I've had one give way once, and it just did it at the bottom, and there was no
I think
flying
that was
glass.
probably a slightly the thickness of the glass we reckon was just slightly less.
Yeah,
than,
it was
you know,
a bit of a flaky tube. Funny enough, that's when we did something for the Naked Scientists, who I think are appearing. They're the closing act, aren't they? Yeah. Right. Got time for a couple more questions. Third row with the beige jacket.
Are you insured for your risk assessments?
Yeah, we went to Direct Line, and yes, we've got £5 million worth of public liability, as will all your schools, presumably. So it's normal public liability insurance.